I'm John Koza from the Computer Science Department at Stanford University. In nature, biological structures that are more successful in grappling with their environment survive and reproduce at a higher rate. Biologists interpret the structures they observe as the consequence of natural selection operating in an environment over a period of time. That is, in nature, structure arises from fitness. One of the central questions of computer science is how to get a computer to solve a problem without being explicitly programmed. In this video, we will show via numerous examples how the structure of a computer program required to solve a given problem can emerge from a simulated evolutionary process. The required program structure will be evolved by means of natural selection, using a fitness measure that determines how well the program does at solving the problem. We will see that computers can be programmed by means of natural selection. A wide variety of problems can be viewed as requiring the finding of a computer program that starts with certain inputs and produces certain desired outputs. For example, the problem of controlling a robot arm so that it reaches out to a given destination point can be solved with a computer program that takes the location of the destination as its input and produces the appropriate motions of the robot arm as its outputs. The multidimensional control problem of backing up a tractor-trailer truck to a loading dock can be solved with a computer program that takes the present location and heading of the tractor and trailer as its inputs and produces an appropriate steering action for the cab as its output. The problem of controlling an artificial ant so that it finds all the food along an irregular trail can be viewed as a problem of finding a computer program that takes the ant's sensor values as its inputs and produces the appropriate moving and turning actions as its output. Determining which of two intertwined spiral a given point belongs to involves finding a computer program that takes the Cartesian coordinates of the point as its input and produces the correct identification of the spiral as its output. The problem of getting an autonomous mobile robot with 12 sonar sensors to locate a box in the middle of an irregular room and to then push the box to the wall involves finding a computer program that takes the 12 floating point sensor values as its inputs and produces the appropriate moving and turning actions as its output. The problem of finding a mathematical expression that fits a given sample of data can be recast as a problem of finding a computer program that takes the value of the independent variable as its input and produces the value of the dependent variable as its output. Of course, recasting problems so that they require finding a computer program is productive only if there's a way to find the required program. In this video, we show such a way. That is, we show how to genetically breed a population of computer programs to solve problems. We do this by applying the Darwinian principle of survival of the fittest and the genetic recombination operation to populations of computer programs. Specifically, genetic programming is an extension of the genetic algorithm originally developed by John Holland, in which the individuals in the genetic population are computer programs. That is, each individual in the population is a computer program composed of primitive functions and terminals appropriate to the problem. A computer program can be represented as a parse tree, in which the functions, such as addition and multiplication, appear at the internal points of the tree, and in which the terminals, such as the independent variable x, appear at the external points of the tree. The Lisp program shown here as a symbolic expression would ordinarily be written as x squared plus x, which in Fortran or C might be written as shown. Genetic programming starts with an initial population consisting of hundreds or thousands of randomly created computer programs. These initial random programs are of various sizes and shapes. In the main generational loop of genetic programming, each program in the population is executed. Its performance in solving the problem at hand is then measured via a fitness measure. For example, the problem may be to find a mathematical expression that fits a given sample of data points from the target curve x cubed minus x. The target curve is colored green here, and the curve produced by the given expression is blue. The difference between the two curves is the error, as shown in red. The smaller the error, the better. After measuring the fitness of each program in the population, A small number of programs are probabilistically selected from the population in proportion to fitness. The reproduction operation then copies them, unchanged, into the next generation. In addition, a large number of pairs of programs are probabilistically selected from the population in proportion to fitness to participate in the sexual recombination operation, that is, crossover. The parents participating in crossover are usually of different sizes and shapes. A crossover point is randomly selected in the first parent and in the second parent. Then the subtrees below the crossover points are exchanged, thus producing two new offspring computer programs. The offspring are syntactically valid, executable programs, which usually differ from both of their parents in size and shape. A new generation of individuals is thus produced. Each individual in the population is executed and measured as to how well it grapples with its problem environment. The reproduction operation and the crossover operation are then applied to the new population, and this iterative process is continued. Over a period of many generations, the fitness of the population as a whole and the fitness of the best single individual in the population typically improve. Eventually, this evolutionary process may produce a mathematical expression that fits the data originally produced by the cubic curve x cubed minus x. The best single individual from the populations is typically designated as the result. Five major preparatory steps are necessary before executing the genetic programming process. The first major step in preparing to use genetic programming is to identify the terminal set. The terminals are the inputs to the computer programs that make up the population. For the problem of symbolic regression of the cubic curve x cubed minus x, the terminal set is just the one independent variable x. The second major step is to identify the function set. For the problem of symbolic regression, the function set might be the arithmetic operations of addition, subtraction, multiplication, and division. Closure is assured by using a protected version of the division function, which handles the possibility of division by zero. The individual computer programs in the population will each be compositions of the functions from the function set and the terminals from the terminal set. The third major step is to identify the fitness measure. Genetic programming, like evolution in nature, is driven by fitness. For symbolic regression, the fitness of a particular individual computer program in the population is measured by means of error, shown here in red, between the value of the dependent variable produced by the individual program and the value of the target cubic function. In this problem, and in many problems, fitness is measured over a number of different fitness cases. Here there are 20 fitness cases, consisting of 20 values of the independent variable x chosen over an interval. Fitness cases are chosen in much the same way as test data for debugging a computer program. The fitness cases must be representative of the problem as a whole, so that the result produced by genetic programming can generalize. The fitness cases represent the environment to which the population is adapting. The fourth major step in preparing to use genetic programming is to select the control parameters. The major control parameters are population size, 500 for many examples on this tape, and the maximum number of generations. Finally, the fifth major step is to specify when to terminate a run and the method of designating a result. For example, we might terminate when the result produced by a program is within 0.01 of the target for all 20 fitness cases, or after a certain number of generations. We designate the best single individual obtained during the run as the result. We have already seen how fitness is measured for the problem of finding the mathematical expression for a given sample of data. The performance of several individuals from the initial random population is shown here, the best of which is shown here. After applying the Darwinian reproduction operation and the crossover operation, the best of generation individual in generation 1 fits the target curve more closely than before. Similarly, the best of generation individual in generation 4 is better than its predecessors, as is the case for generation 5. In generation 6, the best of generation individual is a perfect fit to the data. In genetic programming, the size and shape of the computer program that solves the problem is not specified in advance. Instead, the functional form, as well as any necessary coefficients, evolve under the selective pressure provided by the fitness measure. The best of generation individual in generation 1 consists of 29 points, 14 internal points containing functions, and 15 external points containing terminals. The best of generation 4 has 43 points, while the best of generation 5 has 19 points. In generation 6, the best of run individual has 19 points. Notice that we did not specify in advance that the functional form of the solution was a polynomial, or that the polynomial was cubic. Genetic programming evolved the necessary structure as a result of the selective pressure exerted by the fitness measure. Classification involves classifying objects into categories. In the intertwined spiral problem, there are 97 points on the red spiral and 97 points on the blue spiral. The goal is to evolve a computer program which, given the x and y coordinates of these 194 points, correctly classifies them as belonging to either the red or blue spiral. Fitness is the number of correctly classified points. As one would expect, programs from the initial random generation correctly classify only about 50% of the points. The best of generation individual here partitions the space into horizontal stripes of equal height, the correctly classified points being shown with large circles, and the incorrectly classified points being shown with small circles. After applying the Darwinian reproduction operation and the genetic crossover operation, the best individual from generation 1 partitions the space into vertical stripes of unequal width. The 7-point program of generation 1 is equivalent to the sine of x divided by 0.285. The best of generation 3 scores a little better by partitioning the space into irregular blotches that track segments of the spiral better than mere stripes. The best of generation 7 classifies 152 of the 194 points by combining the vertical stripes from generation 1 with a vertical sinusoidal pattern straddling the vertical axis, as shown here. Notice that the 7-point program from generation 1 is now a subprogram of the new 22-point program. The irregular waves from the best program from generation 10 do even better. The best of generation 35 correctly classifies all but 1 point. The one erroneous point belonging to the red spiral is just barely outside the red zigzag and is therefore shown as a small red circle. The erroneous performance of this 177-point program, scoring 193 out of 194, is caused by the constant 0.304. In generation 36, all 194 points are correctly classified, and the boundary of the red zigzag has moved so as to correctly classify the final point, 35, 36. The crossover operation has inserted the expression x plus y to create this 100% fit 179-point program in generation 36, 35, 36. In the artificial ant problem, food is located along an irregular trail, with single, double, and triple gaps and missing corners. Fitness is the amount of food eaten. Some initial random computer programs merely repetitively move without looking, while others go into an infinite loop when they encounter even a single gap in the food trail, while still others locate some of the food and then actively avoid the food. Eventually, an individual computer program is evolved which enables the ant to successfully navigate the entire trail and find 100% of the food, as shown here, and as shown here as a rooted point-label tree with ordered branches. Backing a tractor-trailer truck to a loading dock is a difficult problem of control, fitness being the distance to the loading dock. Some random truck controllers from Generation 0 cause the truck to turn endlessly, while others cause the truck to drive off into the distance. The best program of Generation 5 manages to move the truck to the wall for certain fitness cases, but not to the place on the wall where the loading dock is located. Later, the truck crashes into the loading dock. However, by Generation 26, a controller is successfully evolved that causes the truck to back up to the loading dock, as shown here. In the foregoing problems, we saw fitness being measured by error, the number of cases correctly classified, the amount of food eaten, and the distance to the loading dock. In the intertwined spiral problem, the functions in the computer programs and the genetic population consisted of various mathematical functions and the if less than or equal to operator. The if less than or equal operator and other similar operators in other problems are implemented as a macro. The numerical constants that you saw were initially created at Generation 0 and then recombined in various different ways in later generation to produce new constants. In the artificial ant problem, the programs consisted of robotic actions, such as moving forward, turning left or right, as well as a food sensing operator. The functions used in the programs for the truck backer upper were similar to those of the spiral. In each instance, natural selection, driven by the fitness measure, produced the program structure needed to solve the problem. In the broom balancing problem, the goal is to find a control strategy for applying a bang-bang force to the cart so as to bring the cart to rest, with the broom standing upright, in a minimum amount of time. The inputs to the computer program we are seeking consists of the state variables of the system. Controllers for the broom balancing problem can be visualized as a control surface that partitions the three-dimensional state space of the problem into parts specifying the direction for applying the bang-bang force. The apparently time-optimal solution evolved by Generation 46 is shown here and is equivalent to this 8-term expression. The succession of ever better programs produced by genetic programming is nothing like the sequence of programs that a human programmer would create while debugging and perfecting a program. In genetic programming, the trajectory through the space of possible computer programs is determined by fitness and evolution. In the wall following problem, we seek a computer program enabling an autonomous mobile robot equipped with 12 sonar sensors to follow the walls of an irregular room. Fitness is the number of zones along the wall that the robot touches within the allotted time. Many of the initial random programs cause the robot to spin around in circles, while others cause it to wander aimlessly, and others cause it to bang into the wall. The wall banger is slightly better than the others because it gets near the wall at one place. The best of Generation 0 scores more by gyrating around the room and is terminated when the allotted time runs out. The ricocheting strategy produced by the best program of Generation 2 has better fitness. The zigzagging trajectory of Generation 9 is better yet, but it is not yet what one would call wall-following behavior. The snake-like trajectory of Generation 14 avoids all unnecessary travel across the center of the room and only misses 7 of the 56 zones along the wall, while the tighter slithering trajectory of Generation 49 only misses 1 zone. Wall-following behavior emerges in Generation 57 via this program. In other runs, solutions were evolved which ran backwards. In the box moving problem, the goal is to get a similar robot to locate a box near the middle of an irregular room and then push the box to the wall. The fitness of a box moving program is the sum, over 4 fitness cases representing different initial conditions, of the box's distance from the wall when the time runs out. When the robot starts in the southwest corner under the control of the best program of generation 0, the robot bumps the box slightly, whereas when the robot starts in the southeast, it never even reaches the box. In this fitness case, we again see the robot merely nudging the box. When the robot starts in the northeast, the robot exhausts itself by pushing against the wall. When the best program of generation 45 takes over, the robot, starting in the southwest, pushes the box to the wall. When the robot starts in the southeast, no box-like prominence confronts the robot, so the robot quickly finds the box and pushes it to the wall. Note that the robot compensates for the rotation of the box caused by the pushing. As we can see from this fourth fitness case, the robot similarly succeeds when it starts off in the northeast. Genetic programming can be used to evolve a minimax strategy for games, such as the discrete pursuer-evader game shown here, and the differential pursuer-evader game shown here. For the games that we have just seen, the strategy was evolved using a fitness measure based on an optimal opposing player. However, for most games we do not have the luxury of having an optimal opponent from whom to learn. Coevolution provides a way out of the dilemma of how to learn a game playing strategy without already knowing it. In this two-person game of complete information, player X starts and makes a move. Play then alternates between player O and X until one of the 32 endpoints of the game tree is reached, whereupon a payoff is received. In coevolution, there are two populations of game-playing strategies. Each serves as the environment for the others. The two grids at the bottom display the relative fitness of each strategy in the X and O population, as a rainbow of colors, with red denoting the best. The relative fitness of a particular strategy is the average payoff obtained when it is played against all or a sampling of the strategies in the current opposing population. Genetic programming is driven by the relative fitness of the individual strategies in the population. As can be seen, the relative fitness of the two populations improve from generation to generation, that is, they get redder. The two grids at the top show the absolute fitness of each strategy in the two populations, as measured against an externally provided known optimal player. Although genetic programming has access to and is driven only by relative fitness, the absolute fitness of the two populations are converging to high values, as shown in red. The strategy that evolved for player X is shown here, and the strategy that evolved for player O is shown here. We test the ability of a genetically evolved robot controlling program to reach any point in the unit square by means of a representative set of destination points, 25 fitness cases here. The considerable shortfall between the endpoint of the robot arm and the 25 destinations are shown here in red. Fitness is the sum over the 25 fitness cases of these shortfalls. The solution evolved by genetic programming to this inverse kinematics problem reaches all 25 destination points. Notice that the computer program involved in this problem has two main branches and returns two values, the angles for moving the two links of the robot arm. Also, in this program, the angle produced by the first branch is available to the second branch for determining the second angle. We sometimes see the emergence of interesting higher-level behavior when a number of independent agents simultaneously execute a common computer program. The 20 independent agents here each have the ability to move, detect the presence of adjacent food, pick up food, and drop food. Initially, the 25 pieces of food are widely separated. Suppose we define the fitness of a particular computer program as the average distance between the 25 pieces of food after execution of that program by all 20 agents for a certain period of time. A highly fit program would consolidate the food into one large clump. As one would expect, even the best random program from generation 0 does not consolidate the food very much. However, after applying the Darwinian reproduction operation and the genetic crossover operation over a number of generations, genetic programming successfully evolves a highly fit computer program which, when executed by all 20 independent agents, successfully consolidates all 25 pieces of food into one clump. Consolidation has begun after only 20 time steps. By time step 100, the food is already congregating in the middle of the screen. Finally, all of the food is in one reasonably compact, contiguous clump. Note that the structure of this genetically evolved computer program is a consequence of the center of gravity type of fitness measure. This more complex illustration of the evolution of emergent behavior is motivated by the central place foraging behavior of ants in nature. All 20 ants here start at the nest. The fitness of the common computer program controlling the ants is measured by how much of the food in the two piles is transported to the nest within the allotted time. In addition to the functions available to the previous independent agents, the ants here can secrete slowly dissipating chemicals called pheromones, and can also detect these pheromones and navigate back to the nest. As one would expect, even the best of a population of random computer programs is not very effective at bringing any food back to the nest. However, in generation 38, the ants begin by searching for food at random and quickly stumble into some food. The ants pick up the food, head towards the nest, and drop pheromones along the way. As the other ants stumble into the pheromone trails, they are recruited into the exploitation of the discovered food. The structure of the 100% effective, genetically evolved computer program being shown here was the consequence of the relentless selective pressure applied by the fitness measure over many generations. This selective pressure led to the preservation of program fragments associated with relatively good fitness, and also led to the genetic recombination of program fragments from parents with relatively good fitness. As you can see, 74 of the 144 pieces of food have been transported by time step 80 of this simulation. Moving quickly forward through time, we see that this program causes 100% of the food to be transported to the nest. That is, program structure arose from fitness. Programs can include operators which iteratively perform certain subprograms until some termination predicate is satisfied. Here the blocks are being unstacked and stacked until they spell fruitcake. Limits are established on both overall time and the time consumed by any one iterative operator. In the next three problems, we will see fitness being measured by the entropy of a temporal sequence of binary digits. Entropy is maximized when the sequence is unpredictable and random. It is difficult to program a good randomizer. The next 16 patterns that you will see are the outputs produced by the best of generation randomizer in the population over 16,384 time steps. Randomization is poor on the early generations. The best randomizer from generation 6 is still noticeably regular. Fitness here is the entropy of the distribution of the 128 subsequences of length 7. If all 128 subsequences are equally frequent, the entropy would be maximal. On generation 0, only a few of the 128 possible subsequences of length 7 are even produced by the best of generation individual, as shown by this histogram. The entropy of this distribution is far from maximal. However, as we proceed from generation to generation, the entropy of the distribution of frequencies of the 128 possible subsequences improves. Starting at generation 7, all 128 subsequences are represented, but their frequencies are far from uniform. However, in later generations, these frequencies do become more uniform, thereby approaching the maximal possible entropy. Here again, the fitness measure, entropy, guided the evolution of the program structure that performed the desired task. A cellular automaton consists of a cellular array of identical automata. The next state of each automaton depends only on its current state and the state of its two neighbors. The goal is to find a state transition rule which produces a high entropy temporal sequence of states for the vertical column containing the middle automaton, the one starting in the red, or on state. Generation 4, like generation 0, exhibits considerable regularity. Entropy is visibly higher by generation 6, and it is difficult to discern any pattern by generation 10. By generation 25, we found state transition rule 30, a known chaotic rule. This 83-point program is equivalent to the exclusive OR of the western neighbor and the disjunction of the center and the eastern neighbor. The temporal behavior of the middle automaton is shown here for the best of generation 0 in the same manner as before, and for generation 4, and 6, and 10, and finally generation 25. The distribution of frequencies of the temporal subsequences of length 4 is shown here for the best of generation 0 in the same manner as before, and for generation 4, and 6, and generation 10, and finally generation 25. The next state of each automaton in this two-dimensional cellular automata depends only on its current state and the states of its four neighbors. The middle automaton starts in the red, or on state. Generation 1, like generation 0, exhibits considerable regularity. Entropy is visibly higher by generation 5, and it is difficult to discern any pattern by generation 7 or 8. A high entropy state transition rule has been evolved by generation 10. The temporal behavior of the middle automaton is shown here for the best of generation 0 in the same manner as before, and for generation 1, and 5, and 7, and 8, and finally 10. The distribution of frequencies of the temporal subsequences of length 7 is shown here for the best of generation 0 in the same manner as before, and for generation 1, and 5, and 7, and 8, and finally generation 10. Genetic programming evolved the necessary structure as a result of the selective pressure exerted by the fitness measure. The best Pac-Man from generation 0 was quickly captured by the monsters. But after applying the Darwinian reproduction operation and the genetic crossover operation over many generations, a Pac-Man is evolved which evades the dangerous monsters when they are nearby, eats an energizer, and then attacks the monsters when they are blue, and opportunistically captures the moving fruit when it appears, and eats ordinary food pellets when there are no other pressing considerations. Programmatic image compression condenses a full-color image, such as the one you see on the screen on the right, into a computer program. On the screen on the right, there are 30 pixels in the horizontal direction and 30 pixels in the vertical direction. Each of the 900 pixels is one of 128 different colors, which we map into the range -1 to +1. The goal is to find the computer program whose input consists of the independent variables x and y, and whose output consists of the values between -1 and +1 corresponding to the colors. The fitness cases here are the 900 pixels. The fitness is the sum over 900 pixels of the error between the color value returned by the particular computer program and the correct value for that particular xy position. The terminal set for this problem consists of x, y, and the floating random constants, denoted here by r. The function set for this problem consists of the arithmetic operations and the conditional branching operator if less than or equal. The all-purple screen that you see on the left is the worst individual from the initial random population, with purple corresponding to a value of -1. The individual at the 25th percentile bears hardly any resemblance to the target image, but it is less purple than the worst individual from generation 0. The median individual from generation 0 achieves its somewhat better fitness from its 2 red patches, red corresponding to +1. The individual from the 75th percentile achieves its better fitness from its substantial red areas. The best individual from generation 0 has a portion of the crescent of the target image. Generation 1 contains a crescent structure in the left part of the screen. The 1 pixel wide pattern down the main diagonal of the screen develops in generation 2. The structure at the top of the screen is beginning to develop in generation 3. As we now proceed from generation 4 to generation 50 at a faster rate, you can see the gradual convergence between the image on the left and the target image on the right. Our goal here being to achieve an approximation to the target image on the right in a condensed form. The screen on the right shows which pixels have a color value within 6 color values of the correct value. These hits are shown in white. For the all-purple, worst of generation individual from generation 0, there were only a few hits. The individual from the 25th percentile of generation 0 did somewhat better, since it was not all purple. The median individual has more hits because of the 2 red patches. The individual from the 75th percentile had even more hits because of its substantial red area. The best of generation individual from generation 0 had even more hits, as shown by the white areas on the screen on the right. As we proceed through the generations, you can see the increasingly large white areas on the screen on the right, as more and more of the 900 pixel score hits. The way genetic programming zeroes in on a target value can be further illustrated by attempting to find the cube root of 2. For this problem, there are no independent variables in the programs. The programs consist only of compositions of the arithmetic operations of addition, subtraction, multiplication, and protected division, and random double precision floating point constants. The fitness of a particular program is the difference between 2 and the cube of the numerical value returned by the program. In generation 0, the cube of the value returned by the best random program in the population of 2000 comes to within 0.0048 of 2. In generation 3, the error is reduced to 0.00041 by a 35-point program. The best program from generation 10 has 47 points, and the error is reduced to 0.000007. The best program from generation 20 has 115 points, and the error is reduced to 0.000001. The best program from generation 30 has 111 points, and the error is reduced to 0.1105. The best program from generation 40 has 101 points, and the error is reduced to 12.086. Finally, the best program from generation 50 has 159 points, and the error is reduced to 0.1303. In other words, the programs got larger and larger as a result of the crossover operation, and thereby got closer and closer to the desired target. The structural complexity increased as the solution evolved. Genetic programming can be used to find the mathematical model for noisy, empirically observed data. For example, a formula for the price level in an economy can be found from the time series for the gross national product and the M2 money supply. Here, data for a particular 20-year period is used to evolve the following program for the gross national product deflator, which in turn agrees with the known exchange equation. Notice that genetic programming discovered both the correct nonlinear model and the correct constant representing the velocity of money. A similar formula can be derived from other 20-year periods. We are all familiar with optimization techniques that find the optimal combination of values for numerical parameters. The conventional genetic algorithm operating on fixed-length strings, for example, may find the single point in a multidimensional parameter space that optimizes a certain utility measure. In contrast, genetic programming provides a means for finding an entire function, including all the necessary coefficients. That is, the result is a functional form rather than a single point in a search space. To illustrate the discovery via genetic programming of a function that optimizes a certain utility measure, consider the anolis lizard of the Caribbean. This lizard scans an area of the ground for insects while perched head down from a tree. Since chasing distant insects wastes time that potentially could be used to catch multiple nearby insects, the question arises as to whether it is desirable for the lizard to chase an insect that appears at a particular location. The required decision function is expressed in terms of the abundance of insects and the sprint velocity of the lizard. Fitness here is the number of insects captured. Multiple Monte Carlo simulations are made over a number of combinations of values of insect abundance and lizard velocity. The best program of generation 0 instructs the lizard, perched at the origin, to chase any insect it sees in the green region and to ignore any insect in the red region. By generation 10, most of the points nearest the origin are colored green, although many distant points are also still colored green. By generation 25, the green area is now bounded and has a generally semicircular shape. The decision function produced by genetic programming is shown here. In a different and more difficult version of this problem, the ground is so hot that the insects always fly away before the lizard arrives in the wedge-shaped region between -60 and -90 degrees. This area is red because the lizard has learned to ignore this region. The remaining close-in region of the bottom half is green because insects are always present when the lizard arrives, as was the case in the first version of this problem. In the top half, the probability of the insect being present when the lizard arrives decreases from 100% to 50% as the angle increases from 0 degrees to 90 degrees. As can be seen, the lizard has correctly learned to chase insects only in the flattened curved area shown in green. In Boolean concept learning, the goal is to evolve a computer program that mimics the performance of a target function, here the Boolean 11 multiplexer function. This scorecard shows the performance of the best of generation individual in the population for each of the 2048 combinations of the 11 Boolean inputs, green denoting a match between the individual and the target value, and red denoting an error. As can be seen, the best of generation individual in generation 0 gets the correct value for somewhat more than 50% of the 2048 fitness cases. However, as we proceed from generation to generation, we see increasingly correct performance, as indicated by the increasingly large number of green marks on the scorecard, so that by generation 9 we have a 100% correct solution. It is instructive to examine the genealogical audit trail to see how crossover created this 100% correct solution in generation 9. One of its two parents from generation 8 scored 1,792 hits, while the other parent from generation 8 scored 1,920 hits. The 100% correct offspring in generation 9 consists of the part of one parent that correctly handles all the even-numbered addresses of the multiplexer, and the part from the other parent that correctly handles the odd-numbered addresses, as shown here. And, as can be seen here, where the sawtooth areas in red denote the first parent's errors, all of which are in the bottom 1024 fitness cases, and where the rectangles in red denote the second parent's errors, all of which are in the top 1024 fitness cases. Typical runs of genetic programming exhibit the same kind of progressive improvement from generation to generation. As can be seen in this run of the 6-multiplexer problem, the zero-based standardized fitness of the best of generation individual, indicated in light blue, and the standardized fitness of the population as a whole, indicated in red, improves from generation to generation. The standardized fitness of the worst of generation individual is shown in dark blue. This pair of curves shows the structural complexity, that is the total number of functions and terminals, in the best of generation program, indicated in red, and the average structural complexity, indicated in blue, of the population as a whole for the same run. The percentage of the population that consists of unique individuals, called variety, is shown here. The hits histogram shows the number of individuals in the population that score a particular number of hits, 0 to 64. The hits histogram demonstrates the progressive learning of the population as a whole. Notice the undulating left-to-right movement as the histograms slink from generation to generation. An interactive display, such as shown here, permits monitoring of genetic programming runs. Progressive change in fitness and hits of the best of generation individual are being monitored here in this particular run of symbolic regression of a quartic polynomial, while standardized fitness is being monitored here. The tree structure of the best of generation individual can be monitored here. The closeness of fit between the target function and the best of generation individual are monitored here. The hits histogram can be monitored here, while the structural complexity can be monitored here. If we apply genetic programming to the problem of learning the even 3 parity function using the function set consisting of AND, OR, NAND, and NOR, and with a population size of 4,000, A typical solution might contain 45 points, as shown here. If we scale up this problem to learning the even 4 parity function, a typical solution might contain 149 points, as shown here. When we continue to the even 5 parity function, we obtain a solution with 347 points, as shown here. However, this unwieldy result was obtained with this population size only after many runs. If a human programmer were writing a program for a higher order parity function, he would probably first define some useful building blocks or subroutines, probably lower order parity functions, such as the 2, 3, or 4 parity. Such building blocks can be automatically and dynamically defined during a run of genetic programming. In hierarchical automatic function definition, functions can be defined on the fly and then called by the result-producing part of the overall program. Specifically, a multi-part program can be defined in which the first 2 branches provide the opportunity to define functions, and in which the final branch is a result-producing branch. The result-producing branch for the 11 parity problem is a computer program composed of the 11 terminals of the problem, the primitive AND, OR, NAND, and NOR functions, and the 2 functions defined by the 2 function-defining branches. The first function-defining branch would typically be composed of the primitive AND, OR, NAND, and NOR functions, and some number, perhaps 2, dummy arguments or formal parameters. The second function-defining branch would typically be composed of the first defined function, the 4 original primitive functions, and some number of dummy arguments. In generation 0 of a run of the 11 parity function, the best of generation individual scores only 1,026 out of a possible 2,048. The best of generation 1 scores 1,031 hits, while generation 5 scores 1,065, generation 10 scores 1,184, and generation 15 scores 1,408. Generation 20 scores 1,640, and generation 21 scores 2,048. Genetic programming evolved the first branch of this 100% correct solution to the 11 parity problem to be a function definition for the even 2 parity function. In the second branch, genetic programming evolved a function definition for the even 4 parity function, using the now available even 2 parity function. Both of these lower order parity functions were dynamically discovered, on the fly, as was the incorporation of the first defined function into the second function definition. The third branch of this 100% correct solution employs both of the dynamically defined lower order parity functions in order to solve the 11 parity problem. You can see this here in tree form. Thus, hierarchical automatic function definition has solved the 11 parity problem. We have thus seen how program structure can arise from fitness using genetic programming. Error-driven evolution includes the symbolic regression of the polynomial x cubed minus x, Boolean concept learning of the 11 multiplexer and 11 parity functions, programmatic image compression, the finding of the cube root of 2, and the econometric exchange equation problem. Cost-driven evolution includes problems of time-optimal control. Payoff-driven evolution includes problems where fitness is measured by food, points scored in a game, or zones along a wall that are traversed by a robot. In classification problems, fitness is measured by the number of instances correctly classified, in effect a variation of error. Similarly, problems where fitness is measured in terms of the shortfall or difference in distance are also variations of error-driven evolution. Certain problems require problem-specific fitness measures. The randomizers illustrate entropy-driven evolution. The use of implicit fitness is illustrated by the coevolution of the game-playing strategies. In addition to the foregoing problems, my book Genetic Programming shows how many other problems can be solved or approximately solved using genetic programming. Some of the other problems include those shown here. Existing paradigms for machine learning, artificial intelligence, self-organizing systems, and induction do not seek solutions in the form of computer programs. Instead, they operate on specialized structures, such as weight vectors for neural networks, decision trees, formal grammars, frames, conceptual clusters, coefficients for polynomials, chromosome strings, and production rules. If we're really interested in getting computers to solve problems without being explicitly programmed, the structures that we need are computer programs. Genetic programming offers a unified, domain-independent way to find the computer program which solves, or approximately solves, a wide variety of problems from a wide variety of different fields. Additional information can be found in my book, Genetic Programming, from the MIT Press.